Okay, so please title your notes chi-squared part 2. You know you're excited to learn cool stuff today.
I won't be here today.
Lame.
I'll be anyway.
How dare you? I'm insulted. Alright, so last week I taught you guys how to calculate chi-squared, and I would say we're fairly proficient at doing it. The way I calculate chi-squared, as a reminder, is I take my observed value minus my expected, divided by my expected, and I square the top. And it gives me a number. And for example, we did a experiment with school absences where you got a data set. We're trying to figure out whether or not absences change on a given day. And we found a chi-squared of 6.3 through plugging it into this formula. But the problem is, how do we know if this 6.3 is actually significant or not? And that's what we're going to learn today, is we're going to get a baseline. Once we get our chi-squared, we can reference these chi-squared distribution tables that are taped onto your desk today. And this is a tool to tell us whether or not our chi-squared is big enough to be significant. And the bigger my chi-squared, what does that tell me about the data?
The weirder it is.
The weirder it is. So if I get a really, really big chi-squared, that means, hey, this is not normal. The results we got in this sample is weird. And then the closer it is to 0, that means it's really close to the expected. All right? So what our good old statisticians have done is they went hard and they're like, all right, we're going to calculate all the chi-squareds I can think of and then map it onto a curve. And what I want you guys to draw in your notes first, title it the chi-squared distribution, and draw a curve that looks like this. This is really important. This is different from the normal curve. This curve is a little bit skewed. So we have a peak here, and then to the right of it, it's like drawn out a little bit farther out. And with the normal curve, right, what we cared about was the area under the curve, like the percent area. And with our normal curve, if we go out 2 standard deviations from the mean, that encompasses 95% of the data. And this is almost the same. We do care about 95%. So the area on this side of the curve is 95% of all the different chi-squareds I could get. And so, you know, I was saying, like, we care whether or not the chi-squared is really big or big enough. The chi-squared that's big enough, we call the critical value. And so I have it written right here, but what it looks like on my curve is this line right here. That represents my critical value. And the way I can think about that is, say I get a chi-squared of like 1, and on this particular chi-squared distribution, it's like right here. Say I get a chi-squared right there. The thing I care about is whether or not this chi-squared I got is to the right of my critical value. If it's not, my results are not significant. That's where I'm going to say, all right, the null hypothesis is true. There is no difference between group A and group B. If, say I got a chi-squared of 22, and it's like way over here, that's weird. So it's just like a normal distribution, where this number is tells you how weird the data is. But the difference is we only care about the right side. Since all chi-squareds are always positive, they're either going to be here, which is still pretty normal, or way over here, which is weird. So the bigger the chi-squared, the more likely it's going to be over here. And our critical value is where or not we say it is significant or not. So for your notes, go ahead and write critical value. And what we're going to say for the definition of it, the critical value, it's a chi-squared value that is big enough to be significant. And our critical value is this here. So we care about all the chi-squareds that are to the right of my chi-squared distribution of the critical value.
And if it's to the left, then the null hypothesis is true.
If it's to the left, it's not significant enough. The null is true. Indeed. All right. So I kind of briefly talked about this earlier in this unit, this thing called a p-value. P-values are the most important thing in statistics. Like, I want you to walk away from this unit just knowing that, oh, if my p-value is less than 0.05, it's significant. Like, I'm going to hammer that in. And so what the p-value tells us is it's the probability of getting an observed value in a normal experiment. So for your p-value, write this definition. The probability of getting a value in a normal experiment. And it's a probability value. And the way I can think about it is, in terms of this graph here, it's actually an area under the curve. So if I were to take my critical value and find the area to the right of it, this would equal 0.05. Or I can think about this as this shaded region is 5% of the area. And that's my p-value, is that area. And one thing that's really important, probabilities, right? We have a way of expressing it. It's like our expected value divided by the total amount of values as well. And that gives us a fraction or a decimal, right? So probabilities in general can be between 0 and 1. They're a decimal between 0 and 1. P-values are no different. So p-values, if I can spell, are always between 0 and 1. So for example, I can have a p-value of 0.42. All right. This is the most important thing, the thing I'm about to write next. And this is like what's super critical for p-values. Now I'm going to put a star next to this. So in order to reject the null hypothesis, my p-value must be less than 0.05. I'm going to box that right there. That's less than. what that means on our graph is my chi-squared is to the right of the critical value on my chi-squared distribution. All right. I just want to check in for a second. And what I talked about so far, give me a thumbs up if you're like, I'm following. Thumbs down if you're like, Andy, you're talking Greek. Sideways? Sideways?
Andy, can you fix your shirt color, please?
It's hard to tell if you're gonna start talking more about exactly what we're doing, or if you're just leaving us to that and just talking.
I know I'm like telling you stuff right now.
So like now he's gonna go over here and say, forget everything we
I'm
just
gonna tell you a little bit more stuff, and then you're gonna practice using the information I gave you today. And hopefully that will make it sink in a little bit better.
No, not gonna.
Or
I'm good.
just resist and observe and.
What, he's gonna walk over here and say, forget everything I just talked
This is an example. Thank you, Vista. What I have written on this board, you do not need to write in your notes. You can if you want to. All right? I just want you to sit and listen for a second. So here's the deal. I'm doing an experiment. I'm testing if a drug causes weight loss or not. And I have two groups. Group A, I'm giving them the real drug. Group B is I'm giving them a placebo. And what a placebo is, it's the fake version of the drug. So the people that are getting tested have no idea if they're taking the real drug or the fake drug. And so I'm doing an experiment. In this experiment, what would be my null hypothesis?
There's no difference
Between what?
the placebo's effects and the real drug's effects on the people.
Exactly. So my null hypothesis would say there is no difference between the placebo and the real drug. What would be the alternative?
The real drug has an effect on the people, because if it's a placebo is not gonna actually affect anything,
Yeah.
besides psychologically.
So the alternative I could say is the real drug causes weight loss.
The placebo, because placebos are used kind of to root out psychological, what people think.
Yeah. All right, so I do this study, I get some data, I run a chi-squared, and I get a p-value of 0.02. What can I say about this experiment? Tristan?
The real drug does cause weight loss,
Because?
because the chi-squared is like to the right of the critical value.
Yeah, we got a p-value less than 0.05. Therefore, whatever I got from my chi-squared, it's over here. Which means, hey, this is significant, guys. And another way I can think about as the p-value is this. If the null was true, there is a 2% chance of observing the result I got. So like, the way I can think about this is, like, if the null was true, if there is no difference between the fake drug and the real drug, and I got the result I got, there's a 2% chance I got that. That's super unlikely. In fact, that is so improbable that that's how we can say it's significant. Does that kind of make sense, that statement there? Really, all I care about is, hey, my p-value is less than 0.05, it's significant. This is just another way to interpret it. Alright? Cool. Alright, the next thing I want to talk about is how do we actually get a p-value from chi-squared. And in order to do that, we need to know this thing called degrees of freedom.
You want us to write this down?
Yep. So write this question down and then title it degrees of freedom. And then on your table, I'm giving 3 out of 4 tables a sticky note, and I would like you to write a number between 0 and 10 on that sticky note. And do not show me. Do not show me.
Does there have to be decimals?
Do not make it decimal. Make sure it's a whole number. One side decimal.
What do I do with it? Andy, I have a genuine question.
Okay, cool.
4 is a good number.
Andy. I have a question. Andy. What is the point?
Hey, Logan,
I
you
just
like the
think,
number?
I don't mind taking
Said just
I'm
any
just
number.
genuinely wondering, because I feel like we never use them.
In order to actually do the content, you need to baseline knowledge, and that's what these notes are for. Is to give you the baseline.
Well, you said any number, right?
I understand that part. Never mind.
Just get rid of
It's
that
not
nine.
fine. I don't mind taking.
Like, you can't do the worksheet
It
that I
can't
have
be a
today
6.
without these notes.
It can be.
Or
But
I
if
have
they're
to-
has to be a
like,
whole
if they're
number,
up
you
on the
idiot.
board, then my answer to why do we need to write them in? I feel like
Fine.
we don't write them.
Happy now.
Writing them is a really good way to
Be
help
happy,
you
okay? You said it. You should have known by giving me the, by giving me.
No, you're going with the pencil. I don't know where my pencil went. It's
It
my,
is a way of like internalizing it better.
there it is.
All right, I got 1 sticky note.
Here.
I got 2 sticky notes. I got 3 sticky notes. What I'm gonna do is I'm not gonna look at them. I'm just. Did you write them big on them?
No.
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 I don't know. You just looked, Andy.
I know. I just. Okay, that
I
totally did
saw
not work.
you.
That did, totally did not work.
Andy, what do you want us to do?
Okay, I was trying to give you guys a example of how to do degrees of freedom. So I got 3 different numbers from 3 different tables, right?
Yes.
Here's my question. I know one thing from these 3 numbers. I know the average of those 3 numbers. Here's my question. How many of those numbers do I need to know in order to know all of them? Do I need to know 1 in the average? Do I need to know 2 in the average, or all 3?
I'm gonna say like, no,
All 3.
I don't
Well,
trust
yeah,
you.
but that's not it.
1,
Nope,
2.
The average.
2. So the thing is, for degrees of freedom, in order for us to know all the information about a sample, I just need to know how many I ever have minus 1. So degree of freedom, where did I put my notes? There they are. What it is it's the number of independent pieces of information. That's the definition of it. So it's the number of independent pieces of information. And the formula I use for that is just this. df is what we call the degrees of freedom. It's just n minus 1, where n is the number of options, or number of pieces of information. So, for example, a dice. How many sides of a dice are there?
6.
6. So I have 6 options. What would be my degree of freedom?
5.
5. Yeah, totally. So dice, it has 6 sides. And then my degree of freedom would just be 6 minus 1, which is 5. Okay, so, I want to look at behind us for a second and see the school absences data that we did earlier. Whoop.
Who's filming?
Vista.
Oh, nice.
Okay, you guys are not quite ready yet, but
What?
Maybe we never are.
It's been rough today, dude.
I know. Alright, school absences. I took data for Monday, Tuesday, Wednesday, Thursday, and Friday.
Is that actual data?
Sure. I got it from an example from video, but
Okay.
I don't know if it's actual data.
Well, I was just wondering if it's when you said that, if you meant you actually took it from our grade or if it's
Oh
just
no,
random.
I'm not that cool. I wish I was that cool.
You could have. That would be so easy to do, though.
I have no
Could have
time.
done that.
So I want to know what's my degree of freedom for the absences data.
Or no.
So I took data for Monday, Tuesday, Wednesday, Thursday, Friday, which means I have 5 total options. You take 5 minus 4.
5 minus 1. 1. It's 5 minus 1, right?
5 minus 1.
Sorry, 5 minus 1. That gives me 4. So my degree of freedom is 4 in this case. All right, so on your table, I want you to look at the little chart I have taped to your table. I'm looking at this thing right here. It says critical values of a chi-square distribution with degrees of freedom. If you look on that table, you see that D, that's our number of degrees of freedom.
Sorry.
And I'm looking at that first row, D1. And then if I go to 0.05, that's the number I care about. That's a critical value. And it says 3.841. What's that? That is telling me is I need a chi-squared of at least 3.841 in order for my data to be significant with a degree of freedom of 1. If I have a coin, what is my degree of freedom?
1.
1. I have 2 options, 2 minus 1, 1. So if I'm doing coin data, I need a chi-squared of 3.841 or bigger in order for it to be significant. Does that make sense?
Yeah.
All right, let's look at the degree of freedom for 4. What's my critical value?
9.488.
9.488. We got a chi-squared of 6.3 for that data there. So what can we say about the school absences?
Insignificant.
Well, the kids don't come to school on Monday or Friday.
Our chi-squared is not bigger than the critical value. Therefore, do I accept or reject the null hypothesis? I accept it, right? And our null for this one was that days of the week, there is no difference in absences. We don't have enough data to conclude that there is a difference. And so that's what we can do with these distribution tables and how we get our chi-squared.
Cool.
I'm feeling like we're a little bit confused.
Maybe
Yes?
Try to go through the problem
Very.
with us or something. I don't know.
Do you guys want to start working individually, or do you want to finish the assignment we started yesterday as a team?
Finish it as a team.
Finish it as a team?
Fully sure.
Okay. What I need from you all is the assignment, does age matter?
It's just enough that I can get you in trouble and go to jail.
Oh, that's
Really,
not.
my phone. Look.
Thank you.
Yep.
Andy, do you want us to stop recording?
I'll keep recording. This is part of the lesson.
Okay.
All right. So Clementina,
Who named her child that?
I don't know, but that's intense.
The guy in the math problem who buys
Clementina.
like 50 oranges.
So Clementina really cares about tipping rates, and she at a restaurant got tipping rates for her mom, who's a waitress at this like fancy restaurant. and she found that 70% of adults tip well. Clementina works at a ice cream store, and she takes a survey of 52 high schoolers, and she found that they get 30 good tips and 22 bad tips from that data. All right, so what exactly am I trying to figure out in this problem? My question is there a difference between adult tippers and high school tippers? Do they tip better or worse? That's what I'm trying to figure out. What would be my null hypothesis?
They tip the
I
same.
don't know how to tell.
Well,
Just like give a bunch of money.
that's not a hypothesis.
This is high school.
High schoolers tip the same as adults. That's my null.
Good because
What
they
would
don't
be
stop
the
and
alternative?
We
High
don't
school
tip.
students have a different tipping rate than adults.
That would be acceptable. I also could say adults tip more
Works
or
for me.
better. Exactly. All right, for number 2, we're trying to find our expected number of tipping rates for the high schoolers. How do I find that?
So when you take 70% of the total tips, which is 52, and then just calculate that, which is 36.4.
Yes. Did you guys hear what Haley just said? We know that adult tippers tip well 70% of the time. So if we are assuming that high school tippers tip the same rate, we're also going to take 70% of our sample of high schoolers. So if I take 70% of 52, the way I can find that is just multiply 0.7 times 52, and what number do I get?
36.4.
I should get 36.4, and that is the expected number of tippers, good tippers, that I would do for my sample. All right? Are we following?
Yep.
Sure.
Great.
Wait, so what? Where would I write that one?
That is the answer for number 2. We calculate chi-squared like this. We take our observed minus our expected, square it, and then divide it by our expected again. What is my observed good tippers in my sample of high schoolers?
22? No, 36.4, right?
Nope,
A 30.
30.
Oh, 30, sorry.
Haley, what's my expected then?
That would be 36.
That would be 36.4. Indeed. So if I just get the chi-squared for this, all I'm going to do is plug these numbers into here. So my chi-squared should equal 30 minus 36.4 squared divided by 36.4. What do we get from that?
1.125.
1.125.
Wait, and that's, where do I write that?
That is our answer for number 3 on this assignment.
I'm so confused. I'm so behind. And wait, and what was the answer number 2 though? Where is it?
Our answer to number 2 was this. This was our answer for number 2.
36.4. That's what I got yesterday when we did it.
Yeah.
But I did not. I got 0.351 for number 2 last time. So I don't know what that's about.
I don't know what you did.
Yeah, I don't know what that's about.
Okay, I'm looking at number 4 now. And it says, what is the degree of freedom for Clementina's data?
Are we looking specifically at their tips?
So,
Or
what's my options?
No, I was gonna ask something else.
What were you going to ask?
If I could go to the restroom.
After I'm done.
Alright, cool.
Either you're a good tipper or you're a bad tipper.
I'm either a good tipper or a bad tipper, so I have 2 options. So what would be my degree of freedom?
1.
1, right? All right, look at your table. I'm looking at number 5 on this sheet. It says, use the chi-squared distribution table and find the critical value. What is the critical value for this data?
Degree of freedom is 1.
For 1 degree of freedom, what chi-squared do I need to get?
3.841.
3.81.
41.
41?
Okay, so how would we write that?
So for number 5, you could say CV for critical value equals 3.81.
CV.
41.
CV equals what?
What? Time, what?
3.841.
3.841 for number 5.
For number 5.
Well, no, what was number 4?
1.
Just 1?
One.
Yeah, because we had 2 options, bad tippers or good tippers.
Okay, bet.
2 minus 1, that is 1 degree of freedom. All right, what would we say for number 5? It says based on the chi-squared.
That's 6.
Oh, what would we say for number 6? It says based on the chi-squared, is there enough evidence to conclude there's a difference between tipping among high schoolers and adults? Is our chi-squared big enough?
Yeah, I think so, right?
What chi-squared did we get in our data?
Oh, never
That
mind.
was amazing.
We got 1.125 for our chi-squared. We need at least 3.841 for it to be significant. So from this data, we are either going to accept or then reject the null. That's a question.
Reject.
Or,
Except,
yeah, sorry.
Accept the null. There is no difference in tipping between high schoolers and teenagers.
high schoolers and teenagers, totally different.
What does it need to be
So except no.
3.841.
And you said high
3.8.
schoolers and teenagers.
Okay,
Wait for this. Wait, hold on.
that's kind of how we use degrees of freedom in the chi-square distribution table. What I want from you guys today is I got this assignment on dice. I would like you to come up, grab this, work on this. If you are confused on the assignment we just talked about, please raise your hand and I'll come talk to you.
And you said high schoolers.
Oh, I'm sorry, Caleb.
Oh.
I told you that 3 times, you didn't hear me.
Selective hearing.
You guys need a motivator.
I was busy